Hello everyone, welcome to this lecture. In this lecture we will continue our discussion regarding how to construct a transitive closure of relations, and for that we will see some graph theoretic interpretation of transitive closures. We will discuss what we call as the connectivity relationship in the graph of a relation, and then we will see a naive algorithm for computing the transitive closure. So, let me start by introducing the connectivity relation. So, imagine you are given a relation R over a set which may or may not be finite. So, your R is a subset of A cross A, and I define this relation R prime R star, which I call as the connectivity relation, and this is basically defined to be the union of different powers of your relation R. Okay. It turns out that as per my definition of R star, an element A I will be related to A j in this relation R star, provided there exists some path of any length of, it may be of length 1, it may be of length 2, it may be of length 3, I do not care about the length. The guarantee is that there exists at least one path from the node A I to the node A j in the directed graph of your relation R. And why so? Because recall in the last lecture we proved this theorem by induction, right. We proved this statement by induction. The statement states that if you have element A I related to element A j in the nth power of your relation R, then that is possible only if you have a path of length n from the node A I to the node A j in the directed graph of your relation R. Now, if I say that A I is present in R star, then it means that either A I comma A j is present in R power 1, or it is present in A I, it is present in R power 2, and in the same way it will be present in some power of R. I do not know which power, but since it is present in R star, and the definition of R star it is that it is a union of all powers of R. So, if A I is related to A j in R star, that means it is present in one of these powers of R, say if ith power, then as per this theorem statement which we have proved in the last lecture, there exists a path of length I from the node A I to A j. It might be possible that A I comma A j is also present in say some other power of R, that is also possible, say it is present in the kth power. That means, as by the same statement there exists a path of length k from the node A I to A j. So, that is why I am not focusing on the path length here. I am just stating here that if at all the element A I is related to the element A j in the relation R star, then some path exists from the node A I to the node A j in your graph of the relation R. Okay. Now, we will be focusing on this connectivity relation, where the relation R is defined over a finite set. That means, R is defined over a finite set consisting of n elements. My claim here is that R star is nothing but the union of R, R square and up to R power n, because you do not need to take the union of higher powers of R. Any higher powers of R will be subsumed in the union of the first n powers of R, provided your relation R is defined over a finite set consisting of n elements. And this is because what can be the maximum path length between any two nodes? Remember, in the graph of your relation R, you have n nodes, because now the relation is defined over a set consisting of n elements. Okay. So, what can be the maximum path length? The maximum path length can be n only, okay, because you have only n distinct nodes possible. Of course, you can keep on traversing along this path again and again and again, that will be considered as a path of a higher length. But what do I mean by maximum path length? By maximum path length I mean here maximum path length where path has distinct edges. And why distinct edges? Because if I say for instance consider r power n plus 1, that means I am interested to find out whether there exists a path of length n plus 1 between any two nodes in the graph G. Well, since I have only n distinct nodes possible, then the path of length n plus 1 is possible only if a node is repeated in the path. That means, say for instance, I have a path of say n is 3, okay, okay, or say n equal to 4, say, okay. So, I can say a path of length 5 exists between A1 to A2, because I can go from A1 to A2, that is 1, then A2 to A3, that is 2, then A3 to A4, that is length 3, and then A4 to A1, that is 4, and then again from A1 to A2, that is length 5. Okay. But the same path can be considered as a path of length 1, because you have the node A1 to A2. So, what I can say is that both A1 comma A2 present will be present in the relation R, and the same A1 comma A2 will also be present in R power 5. The same A1 comma A2 will also be present in R power 9 and so on. So, when I will be constructing R star, which will be union of R and R4, then anything which is present in R power 5, R power 9 and so on, say for instance this element A1 comma A2 which is present in R power 5, R power 9 would have been already subsumed in R itself. I do not need to separately consider those pairs by considering the fifth power of R and so on, because I know that I can't have a path of length 4 consisting of, I can't have a path of length more than 4 consisting of distinct edges. If at all there is a path of length more than 4, that means some edges and nodes are repeated, that means that path by excluding the repeated edges and nodes would have been already counted in some lower power of R when I would have constructed R star. So, that is why when my relation R is defined over a finite set consisting of n elements, then to construct the connectivity relationship, I just need to focus on the first n powers of relation R. There will not be any extra ordered pairs beyond this n different powers of relation R which are present in R star. Okay. So, we have not proved in details, but intuitively this is the statement. Sorry. So, now what we are going to prove here is, now we are going to see a relationship between the transitive closure and the connectivity relationship. So, remember in the last lecture we saw an example where we constructed the transitive closure of a relation, and there we iteratively apply the process, the rule that if you have A comma B and B comma C in the expanded relation R or in the original relation R, then you add the element A comma C, and we keep on doing this process till we do not need to add any extra elements of the form A comma C. So, now what we are going to do is, now we are going to formalize that process by stating this beautiful result that the transitive closure of your relation R is nothing but the connectivity relation. Now, to prove this theorem, we need to prove several things. The first thing that we have to prove is that the relation R, the original relation R, is present in your R star, because that is one of the requirements of transitive closures. that your original thing should be, original relation should be present in the closure of that relation. But it is easy to see that the original relation R will be a subset of R star, because R star is nothing but R union the higher powers of R. So, your original R will be definitely present in R star. So, all the ordered pairs which were there in R will be present in R star. The second thing that we have to prove is that indeed this expanded relation R, which is R star, is satisfying your transitivity property. And for proving that this relation R star is going to satisfy transitivity property, what we are going to do is we are going to show the following. You take any arbitrary a comma b and b comma c which are present in R star, then you have the guarantee that a comma c is also present in R star. Why I am going to show it for arbitrary a b and arbitrary b c? Because the property of transitivity property is the transitivity relationship. The demand is that for all a b c, if a b and b c are there in your relation, then you need a c to be in your relation, and this need to be shown for all a b c. But we can't take every possible a b c in R star and show this implication to be true. So, that is why we are going to show it for arbitrary a b and arbitrary b c, and then take the help of universal generalization and conclude that the statement is universally true for all the elements of the domain. So, assume to prove this implication we have to show that the left hand side or the premise of this implication is true, and then we have to show that even the conclusion is true. That is how the definition of implication given, right. So, assume that a b is present in R star. That means as per the definition of R star, a b is present in some power of R, say the jth power, okay, because that is the definition of R star. And in the same way, imagine that b c is present in R star. So, that means it is present in some power of R, say the kth power. There need not be any relationship between j and k, j could be anything, k could be anything. Now, what I can say here is that the tuple a comma c will be present in the j plus kth power of R, because that is the definition of j plus kth power, because the j plus kth power will be nothing but the j plus kth power of R will be nothing but R power k composed with R power j. That means, you would have applied the relation R power j first. That means, you will say, let us say a b is there in R power j, and on top of that you will apply the relation R power k. So, here b is acting as your intermediate element. So, a b is present in R power j and b c is present in R power k. Hence, you will conclude that a c is present in the j plus kth power of R, and j plus kth power of R will be included in R star, because that is the definition of R star. So, we proved this implication to be true for an arbitrary a b c, that shows that the relation R star is transitive. So, we have proved, we have shown that two of the requirements of transitive closures are satisfied by your R star relation. Now, we have to prove the important thing. We have to prove that R star is the smallest possible expansion of your relation R, which is transitive. And the way we are going to prove this is as follows. So, we have expanded our relation R to R star. We have shown that R is present in R star, and we have also shown that R star is transitive. Now, we have to show this third property. How we are going to do this? We will do this by showing that you take any transitive relation which includes R. That means, you take any expanded version of R which is transitive. In that expanded version of R, namely S, R star is present. Okay. That will automatically show that R star is the smallest possible expansion. That means, there is no smaller subset of R star which includes R as well as it is transitive. That is what we are proving here pictorially. That means, it is not the case that you have something of the following happening, that you have R star and you have say an expanded R, say S, which is transitive and which includes R. That is not going to happen, such that S is present in R star. That is not going to happen. We are going to prove it other way around. We are going to show that you take any transitive relation which is expansion of R, R star will be definitely present in that expansion S, and that automatically will show that R star is the smallest expansion that we have to do. So, more formally we have to prove that you take any set S, any relation S which is a transitive relation such that R is included in S, then the expanded R, namely the connectivity relation, is included in this expanded relation S. So, to prove this property, we are going to take help of a very small fact regarding the transitive relations, and that fact is the following. My claim here is that if S is a transitive relation, then you take any power of that transitive relation, it will be a subset of the original relation. And since this is a universally quantified statement for all n greater than equal to 1, we can quickly prove it by induction. The base case is obviously true, because S is always a subset of S. Let the statement be true for n equal to 1 to k, and now we are going to prove it for n equal to k plus 1. So, imagine you have an arbitrary AC element a comma c present in the k plus 1th power of S. Then as per the definition of S power k plus 1, you have some intermediate element B such that A is related to B in the relation S and B is related to C in the relation S power k. Then I apply the inductive hypothesis here. Since B comma C is present in S power k and the statement is true for n equal to 1 to k, that means this B comma C is present in S as well, because S power k is a subset of S as per my inductive hypothesis. So, now if I have AB present in S and BC present in S, right, I can say that AC is also present in S, because my base case or the hypothesis of the statement that I am proving is that S is transitive. Okay. So, this is a very straightforward fact regarding the transitive relations. If your relation is transitive, you take any subset of that, any power of that relation, it will be always included in your original relation. Okay. So, we have proved it for all n greater than equal to 1. Now, I apply the definition of S star. What is S star? S star is going to be S power 1 union S power 2 union S power n union higher power of anything. So, each of these powers is included in the relation S, because that is what we have proved. We have proved for all n greater than equal to 1, S power n is included in S. So, if you take the union of all the powers of S, that will be included in S, and that shows that the connectivity relationship satisfies the property that if your original relation is transitive, then the corresponding connectivity relationship is included in the original relation. So, that is the side result which we are going to retain here. Now, coming back to the statement that we want to prove here, we want to prove that if you take any transitive relation which is an expansion of R, then the connectivity relation of R is included in that, is going to be included in that expanded R. Okay. So, we have to prove this subset relationship property. So, the definition of subset is that if you have any A comma B present in R star, I have to show the same A B is present in S as well, provided the hypothesis of this implication is true. So, I take an arbitrary A B and assume it is present in R star. Okay. Then since it is present in R star, it will be present in S star as well. This is because as per my hypothesis here, R is a subset of S. That means R square will be a subset of S square. that also means r cube will be a subset of s cube and so on. You take any power of r, that will be a subset of the corresponding power of s, right. That automatically shows that r star is a subset of s star. So, if AB is present in r star, it will be present in s star as well. But you are also given the hypothesis that S is a transitive relation, and if S is a transitive relation, then you take S star, it will be a subset of S itself. That means, whatever is present in S star, it is bound to be present in S as well, right. Hence, we have shown that if AB is present in R star, it is present in S, and we have proved the third requirement of the transitive closure as well. Okay. So, this is a very important theorem which we have proved now, and the theorem is that the transitive closure of the relation is nothing but its connectivity relation. So, this connectivity relation has got significance here. So, let me show its significance. So, imagine you are given a relation R, and R star is defined to be the union of different powers. So, if you interpret the connectivity relationship in terms of the directed graph representing your relation, then what I can say is that AI is related to AJ in this connectivity relationship if AJ is reachable from AI by some path, right, because AI comma AJ present in R star means it is present in some power of R, say the nth power. That means, I have a path of length n from the node AI to the node AJ. That is what we have proved, and abstractly we can interpret it as if in the graph of your relation R, the node AJ can be reached by some path from the node AI. Now, the interpretation of this path depends upon what exactly is your underlying relation. So, for instance, imagine A is the set of all computers in a university, and I define a relation between two computers as follows. I will say that computer AI is related to computer AJ if there exists a direct link between computer AI and computer AJ. That means, AI can directly send a message to the computer AJ by the channel or the cable through which the computer AI is connected to computer AJ. Then, if I construct the connectivity relation R star for this given relation R, then it is easy to see that R star will have all ordered pairs of the form AI comma AJ, where AI is connected to AJ maybe directly or through intermediate computers. That means, R star basically talks about all interconnected computers in your university. Now, let me give you another example of this connectivity relationship. So, have you ever wondered that how Facebook computes new friend suggestions? So, imagine A is the set of all Facebook users, and I define a relation between two Facebook users as follows. I call that relation as R. I say that user AI is related to user AJ provided AI and AJ are mutual friends of each other, are mutual friends over Facebook. Okay. Now, if you take the relation R star with respect to this R, namely the connectivity relationship defined over the relation R over the Facebook users, then if you have AI related to AJ or AK in the relation R star, that means I can say there are series of a sequence of intermediate Facebook users such that AI is related to the first user, then the first user is related to the second user and so on, and the second last user is related to AK. That means, in terms of a graph theoretic property, you can interpret that there is a path of some length from AI to AK, right. That means, even though AI and AK may not be mutual friends, what Facebook can think is that it might be the case that AI has not searched for the Facebook user AK and vice versa. So, let us send a suggestion to AI that, well, you know the user AK or not, and similarly to the user AK, right, because AI is directly related to some A the user A is related to user B, the user B is related to user C, and say there is by sequence of intermediate users you have AI related to AK. And since friendship is by default considered to be transitive, and of course there might be exceptions as well where A is friend to B and B is friend with C, but A need not be friend with C. That is why Facebook just give you a suggestion that hey, looks like that we have found someone who is related to you by some intermediate users, and that is how and to do that basically the Facebook algorithm has to construct here the connectivity relationship of this relation R. Okay. So, this connectivity relationship has got a huge amount of significance. Now, the question is how we algorithmically compute this connectivity relationship. So, we will be focusing on the case when the relation is over a finite set, and recall that in this case R star is nothing but the union of first 10 powers of R. So, what we are going to construct is we are going to construct the Boolean matrix M R star. So, it will be an n cross n Boolean matrix representing your connectivity relation R star, where the ith row and the jth column will be 1 provided the element A I is related to A j in the connectivity relationship R star. So, the question that we want to address here is that you are given the original relation R, namely the Boolean matrix representing the relation R. How you compute the Boolean matrix representing the relation R star, where the relation R is defined over a set consisting of n elements. So, here is the naive algorithm for computing the matrix for connectivity relation. We compute the matrix for different powers of relation R. So, we are already given the relation for R, we are already given the matrix for the relation R. So, we do not need to compute that. So, that is why for I equal to 2 to n we compute the matrix for the next powers of R, and this we can compute by performing a Boolean matrix multiplication operation, which I will discuss very soon. And here what I am going to do is to compute the matrix for the ith power of the relation R. I am going to multiply the matrix for the original relation along with the matrix for the I minus 1th power of the relation R, provided I have already computed it. And then what I am going to do is I am going to take the Boolean disjunction of the individual n cross n matrices for the different powers of R that I have computed, and that will help me to get the Boolean matrix for this connectivity relation R star. So, now there are two operations here, the Boolean matrix multiplication and the disjunction operation. So, I am going to define them one by one. So, let us start with this Boolean matrix multiplication here. So, the goal here is the following: you are given the relation R or equivalently its matrix representation, and say you have already computed the matrix representation for the I minus 1th power of R. And now your goal is to compute the matrix for the ith power of the relation R. So, recall as per the definition of the ith power of the relation R, A I will be related to A j if you have A I related to some A k in the relation R, and A k is related to A j in the relation R power I minus 1. That is what is the definition here. Okay, so, that is what pictorially I have represented here. If that is the case, then you will say that A I is related to A j in the ith power of the relation R. So, basically this we have to check whether this structure is present in the graph of relation R or not. If this structure is present, then we can say that A I is related to A j. Now, how do we check this structure? So, we focus on the matrix for the relation R and for the matrix of the I minus 1th power of R. And my claim is to check whether AI is related to AJ or not, it is sufficient to take the Boolean dot product of the ith row of matrix MR and the jth column of the matrix of I minus 1th power of R. This is because if you take the Boolean dot product, this I comma 1 will be multiplied here with the entry 1 comma j, and multiplying here means conjunction, because remember the matrix MR and the matrix MR of I minus 1 both are Boolean matrix, they just say whether something is related to something or not. So, I can say that if in my graph the element AI is related to element A1 and if element A1 is related to element AJ, then I can say that element AI is related to AJ. So, that is what is the essence of checking this first conjunction, checking whether AI comma A1 is related in the relation R or not, and whether A1 comma AJ is related, A1 comma AJ is present or related as per the relation R of R power I minus 1 or not. If that is the case, I do not care for the other expressions in this overall expression. I can simply say that the I comma jth entry in R power I should become 1, or I should check in the similar way that AI is related to say A2 and 2 is related to J or not. So, that will be the essence of second conjunction here. In the same way, I should check whether AI is related to AK in the relation R and K is related to AJ in the relation R power I minus 1 or not, and in the same way that will be the essence of this kth conjunction, and in the same way I should check whether AI is related to AN directly and AN is related to AJ or not in the relation R power I minus 1. If any of these n conjunctions hold, then I can say that definitely AI is related to AJ in the relation R power I. But if none of these n conjunctions are true, then disjunctions of n zeros will be zeros, and that is why the I comma jth entry will remain 0, right. So, you can see here that if you are given the matrix of relation R, the Boolean matrix of the relation R, and if you have computed the Boolean matrix for relation R of R power I minus 1, then to compute the I comma jth entry. So, let me write down, to compute I comma jth entry of MR, you need to perform order of n Boolean operations, because you will be performing the dot product of a matrix or dot product of two vectors of size n, that will take you order of n effort. And how many such I comma j entries are there that I need to compute in the matrix of R power I? There are n square entries. So, that is why it will be order of n cube computation. So, now coming back to the naive algorithm, the first step was computing the matrix for the different powers of R, starting from the Boolean matrix of the relation R, which is given as an input to U. So, that is why by applying the Boolean matrix multiplication operation that we have discussed just now, we can compute the matrix for the individual powers of the relation R. And now what I have to check is, I have to check whether AI is related to AJ in any of these n powers of R or not. And for that I just need to check whether AI is related to AJ in matrix R of R power 1, or whether AI is related to AJ or not in the matrix of R square, or whether AI is related to AJ or not in the matrix of R power n or not. So, I have to just perform disjunction of n Boolean entries to find out the status of A I comma A j in the matrix of R star. So, it turns out that the first operation here, namely computing the powers of computing the matrix of different powers, will cost me O of n power 4 effort, whereas computing the final matrix of R star will cost me order of n cube Boolean operations. So, now the question is, can I reduce the overall cost here to O of n cube, right. So, we have this naive algorithm of computing the matrix for connectivity relationship, which cost me O of n for n power 4 efforts. My goal will be to do it with order of n power cube Boolean operations, which we will do in the next lecture. So, just to summarize, in this lecture we introduced the connectivity relationship of a relation, and we saw that the transitive closure of any relation is its connectivity relation, and we discussed the naive algorithm for constructing the connectivity relationship for a relation defined over a finite set. Thank you.